Hey everyone, Dr. Chem here, and let's just dive straight into this explainer. Today, we are completely transforming our screens into a high-stakes analytical laboratory to uncover exactly how nutritional labels get their salt data. Consider this your virtual lab masterclass, where we're going to walk through the complete scientific method together, from the basic theory all the way down to the final real-world results.
To keep us on track today, here's our virtual lab manual. We'll cover the role of salt, the science of detection, lab materials and setup, preparing the food sample, executing the experiment, and finally, calculating those final results.
All right, kicking things off with Section 1, the role of salt well beyond just the flavor.
So we all know the World Health Organization recommends a maximum daily sodium intake of 2 grams for adults, right? It's crucial for preventing cardiovascular disease. But here's the big question we actually face in the lab. How do we find it? How do we precisely measure this stuff when it's baked, heavily processed, and just completely blended into the complex matrix of our everyday food? And this right here brilliantly illustrates exactly why all of this matters so much. You know those low sodium or reduced salt labels you see while walking down the grocery aisle? Well, they aren't just some clever marketing spin. No way. They are legally binding claims, and they are the direct result of rigorous, verified chemical analysis done in registered labs. Basically, we have to prove the math.
Okay, before we officially put on our lab coats, we've got to make a really strict chemical distinction. While sodium is the specific element linked to those blood pressure concerns, we are usually looking for it in food in the form of sodium chloride, what we commonly call table salt. So they're related, absolutely, but chemically speaking, they are two totally different targets.
And look, salt isn't just thrown in there to make things taste, well, salty. Food formulators use it for some incredibly complex chemical reasons. It literally controls yeast fermentation rates in bread dough, it binds water in cheeses to give them that perfect firm texture, and it extends shelf life by stopping microbial growth in its tracks. So simply pulling salt out of a recipe requires some serious food science magic, which makes accurately tracking its replacements absolutely critical.
Moving right along to Section 2, the science of detection, and how we choose our method. So we basically have two main investigative routes we can take here. On one hand, we can calculate salt indirectly by measuring the chloride ions. That's typically done through a chemical reaction process called titration, where we use a known solution to uncover an unknown concentration. Or, on the other hand, we can look directly for the sodium ions themselves using super high-tech methods like flame photometry or ion-selective electrodes. For today's explainer, though, we're going to heavily focus on that first one, the highly reliable automated titration method.
Which brings us to Section 3, lab materials and setup, gathering our reagents.
All right, if we're going with the titration method, we absolutely need our primary chemical actor, a 0.1 molar silver nitrate titrant. Plus, we'll need ultra-pure reagent-grade water. And here's a really fascinating detail. Depending on the specific food we're testing, like, say, meat or dairy, we might actually need these specific chemicals called Chemora solutions. What they do is strip away interfering proteins so they don't clog up or block our sensors during the actual test.
Next up, Section 4, preparing the food sample or breaking down the matrix. Okay, ketchup. Ketchup is a fantastic example of a really tricky, thick liquid sample. We can't exactly just drop our super-sensitive electrodes into a thick dollop of ketchup and expect an accurate reading, right? No, we have to physically break it down and isolate that soluble salt into a clear liquid form first. So let's see how this actually plays out on the bench. Following our manual, we carefully weigh out exactly 25.0 grams of our ketchup. Then we blast it with our reagent-grade water and mix it thoroughly for 2 full minutes to get that salt to completely dissolve. Once all the thick solids settle down at the bottom of the beaker, we very carefully pipette out only the clear liquid resting on the top layer. That clear liquid, that's what we actually test.
All right, Section 5, executing the experiment, the automated titration.
Now, to pull this off properly, our machine needs some very precise instructions. Whether we are measuring by weight for solids like cheese or by volume for thin liquids like clear soups, we've got to pre-program our titrator parameters. For instance, we set it to dispense a maximum of 10 milliliters of our silver nitrate titrant. We definitely don't want to waste expensive chemicals if we don't have to. Honestly, the true beauty of automated titration is just watching this sequence play out entirely on its own. The machine drops a stirrer into the sample for exactly 5 seconds, just to ensure a perfectly even distribution. Then it precisely drops in the silver nitrate.
And as that chemical reaction happens, a highly sensitive electrode instantly detects the exact millivolt change in the liquid. It literally pinpoints the precise chemical equivalence point, totally removing the risk of human error. Finally, we reach Section 6, calculating final results, turning raw data into the nutrition labels you actually read.
Okay, listen closely, because if you take away just one number from this entire explainer today, make it 2.54. This is absolutely crucial. It's our atomic ratio factor. See, because the atomic mass of salt is 58.44, and the atomic mass of sodium alone is 22.99. Dividing them gives us roughly 2.54. So we simply multiply our raw sodium content by this exact number to convert it into the equivalent salt content for labeling.
Now, what if we had used a flame photometer instead? That's a brilliant piece of equipment, by the way, really often used for checking sodium in things like fried corn snacks and potato chips. Well, we'd use a very precise mathematical formula. We plug in our dilution volumes, the photometer's reading, and the original sample mass, and boom, it spits out our final milligrams of sodium per 100 grams of product.
And just look at these deeply satisfying real-world results from an automated lab setup. Ketchup is sitting right at roughly 2.8%. Salsa is a bit lower, but check out soy sauce. Our titrator proves it packs a massive 16.73% salt content. And what's really impressive here is that the machine generated these exact, highly reliable results in under 3 minutes of analysis time. Talk about efficiency. So we've completely demystified exactly how scientists hunt down salt in the lab. But the whole landscape is constantly shifting. With brand new bitter taste masking agents, potassium substitutes, and radical micronization technologies constantly hitting the market to secretly lower sodium in our favorite snacks, it really leaves you wondering. As the food industry gets smarter and smarter at hiding flavor, what complex chemical puzzle will our labs have to solve next? I'm Dr. Chem. Thanks so much for joining me at the bench today.